Yeah, if it doesn't look very much Spanish to you, it's my native background is Norwegian. That's why I had this weird name in the last Sortehaug, which means black girl in English. Anyway, first of all, I want to thank the elderly and all the conference delegates. It's okay? Yeah, it's better. Thanks. Thank the elder and all the participants in the conference for taking the time to be here. Secondly, I will also thank the Safe Drinking Water Foundation for inviting me. I will also thank Yellowquill, First Nation, and Dr. Hans Petersen for supplying me with some of the presentation material, as well as Dr. Frank Rogala from Black and Veatch and Dr. Peter Jensen at the Agricultural University in Norway. The question is, can modern technology ensure safe and clean water for the future? I understand yesterday from the talks that some of you was a bit concerned about all the pesticides, all the PCBs, all the stuff that is in the water, and doesn't really encourage us to have the guts. Well, it might do encourage us, but it's sometimes a bit depressing to see all the stuff that is in the water. And it sounds like a tremendous big challenge. Ian Wright gave a very broad perspective of the solution. I will give a very narrow-minded perspective. I will take part of one of the elements that I think could bring us forward. Just to give you a sort of positive injection that there is a lot of challenges out there, yes, but there are also ways to solve them. I think by a robust, compact biological treatment to purify drinking water and wastewater, it's a feasible way to go. One of the feasible ways to go, if you combine it with membrane and reverse osmosis. A wise man in India, Mr. Gandhi, said that the mosaic is the truth is like a mosaic, and if you have one part of the mosaic or one part of the truth, he will be happy. No comparison at all, but if I also can give one part of the truth, I will be happy, not to waste the time. So what is biological filtration then? Well, as you heard over the last 2 days, it's the use of bacteria to purify drinking water and also wastewater. There are compounds that the bacteria can use to gain energy, and nutrients can be removed from the water. To show you some examples that you also have seen from earlier presentation, what you can remove biologically are iron, manganese, arsenic, ammonia, phosphorus, and dissolved organic matter. What is needed then to have this biological filtration? Well, the previous presentation, as you saw, which is a bit more fancy than my one, with a lot of videotapes that I haven't included in mine. Apologize for that. You need water and you need bacteria. And you also need compounds that bacteria can use to gain energy and nutrients to grow. And the idea is that you have no nasty chemicals, such as chlorine. To have these bacteria to work well, you need a home for these guys. You need to provide like a hotel for the bacteria, and you got to provide the right conditions for them to thrive and to be happy. Well, you all just seen a video of that, so I don't have to extend that. And you also need a combination of biological and physical chemical processes. What you see here on the upper part is immobilized bacteria inside porous media, which shows you that there's a lot of cavity, a lot of space to live and thrive, to work on. What kind of stuff can you use then to make a home for bacteria? Well, you can use surface of sand grains that you have done in hundreds and thousands of years, which is an additional natural way to treat it. You can use more advanced material like granulated activated carbon, or you can also use other natural material with a very high porosity to speed up the process. What would you need then for these filter media requirements? Well, you would need definitely a high surface area for biofilm growth so that you can squeeze your process to a smaller unit. In case you want to backwash it, you also need a high resistance to mechanical and or chemical impacts to avoid that the media is falling apart and it can have a long lifetime. If you also can recycle and reuse, that would also be definitely better. So why should you use biological filtration then? Well, one of the key ideas is that you have low or no use of chemicals. You also have a production of better quality water than chemical physical water treatment methods, And from our experience, we also see low levels of failure, and it's a pretty robust, simple system. We even down to temperature to +1 degrees. You have a lower life cycle cost compared with chemical water treatment system, and it's a so-called green technology. It's not like the green micro slime you saw, that's not why it's called green. It's a sort of sustainable technology with natural material, which also can be found locally. The idea is to have a production of biological stable water. This means that you have no bacterial regrowth in the distribution system, which is important for you as plant operators. And you will have less or no fouling of water treatment equipment such as membranes, which you will see in the next photo, that this kind of nasty mess inside the distribution system is exactly what you don't want to have. And if you allow a lot of organic compounds to go into the system, into the distribution system, well, this might be a worst case scenario, but it's definitely not desirable to have those microbes inside the distribution system. If you look at the membrane, you can also see that. You can have a passover by organic compounds into the membranes, which will lead you up to this photo, which is also pretty expensive, since you have to remove the old membranes and replace them. You can see there a photo on a cutout membrane. They have the extensive biofilm growth inside the membrane. So membranes, the actually only way to destroy a membrane is to kill it. Because the membrane as itself, if you treat it only with, if you feed it only with clean water, it can last for probably much longer than I will last. But if you really want to destroy it, you have to kill it. That means you have to push in a lot of organic material so it doesn't work. This photo is familiar to some of you. I will not dwell with that. I will show you the photo of the plant. For those who haven't been there, it's a very nice, it's a very modern plant, it's a very neat plant. As soon as you enter in there, it's a place you like to be there. And that's a good thing with a water treatment plant. It doesn't have to be a boring site that is not attractive. I think it's a very modern, one of the most modern facilities I've seen in the water industry, what you have in Jalakville. I heard some observations yesterday from some of the people that Dr. Peterson talked about some bugs inside that, and bugs, well, people not like that kind of much in the bugs in the water. So, but if you tell those people that if they watch what happened to apple core, if you leave it outside on the ground, after some weeks or months, you will see it will slowly disappearing. And it's not actually the same thing that's happening in the biological contactor tank, but there are bacteria that are removing components that we do want not to have in the water. So if people don't get scared to seeing an apple core disappear, they should not be either scared to see ammonia or iron be removed from the water either. Besides that, you can see the photo, the winters in Canada are long, as in my country. The contact time of inside the biological reactor is around 30 minutes though. And the oxygen consumed at that time is similar to what is happening in the Canadian lake from late November until beginning of March. If you see the oxygen consumed in a 100 days period of time, it will be similar to what's happening in the same contact reactor in 30 minutes. That means the process is around 5,000 times faster, to give an idea about how compact it is. It's an integrated plant. Some of these photos you have seen from early presentations, so I will just pass through. The biological filtration alone is called a secondary filtration. It's not the solution. It never claims to be the solution, but it would probably could be a part of the total solution. So what we can see that could be removed from the biological part is that you can have a high reduction of iron. You can also have a high reduction of arsenic. All the biological organic material could be removed. And you will also have a pretty good oxidation of ammonia, nitrate, which I know is a problem without the many First Nation plants, that you have a high level of ammonia. And you can also have a significant reduction in particles. Well, it's like a horse and a wagon. The biological part combined with a membrane. It's like if you want to carry out a lot of load, if you use both the horse and the wagon, you can carry much load, then you only use a horse and only wagon. So supported by the membranes, after a biological treatment, you can almost remove all the elements that is in the water. You can have a very good reduction of TDS, the sulfates, non-biodegradable organic material, manganese, and alkalinity. You could also remove this manganese in the biological treatment, but the way the process is set up in Jellicoe is preferred to move the manganese inside the membrane rather than in the biological treatment. Because to move the manganese, you have to take away all the ammonia before you start to do that. The very fascinating plant at Jellicoe is very nice. It's very new in its size that it's treating groundwater, and it's the first in Canada. And, but there still are some other treatment plants around the world. This is in the heart of Paris, which has been operated in 1997, and it supplies drinking water to the city of Paris. Another drinking water treatment plant is supplying to 20% of the population in Hong Kong, and that is a pretty huge plant. They had very severe problems with ammonia because they had the technique that they've used in chlorine, with the breakbone chlorine. So they had to use approximately with existing technique like 35,000 kilos of chlorine required every day. And that's a lot of hazardous stuff to transport in one of the highest densely populated cities in the world. So they were happy to go on with biological treatment as a key element to remove ammonia. They have hardly any chlorine used compared to the initial volume. And this plant is extended to be around 1,200 million liters of water per day. So that's a very, very big plant. So the yellow quill plant is, yes, don't use, but there are other plants that is shown that this technology could also work elsewhere. Biological filtration is also referred to as a biological aerated filtration. That means there's a filtration going on, and it's a biological process supported by oxygen. It's also used for sewage treatment, and it's based on the same principle that you have attachment of the bacteria to the solid surface, similar to what we have seen in drinking water. So where can you apply the biological filtration? Well, it could apply anywhere that you have water to treat, water coming in and water coming out. You can use it for individual homes, you can use it for small community or clusters, or you can use it for large communities. This could be a house in a typical First Nation in Canada. The photo is from Norway though, but you could probably have a similar thing here. What you see here is the septic tank, which is always requested. And then you have a pump that is pumping material into a pre-filter biological pre-filter unit. And then you have a filter bed for a final polishing. And if you want to ensure the quality is good, you can have a inspection well here. If you don't want to ensure the quality, you skip the well, but you have no idea what's coming out. So the filter bed itself is called a subsurface horizontal filter bed. It's designed that way because normally filtration will be vertical. In this case, you try to have a horizontal flow to have extended treatment. The first part here in the upper right corner would be the pre-filter unit, where also the intermittent dosing of the feed is very important. When you go back to this, you can see a lot of small house communities plant that you can talk about biological filtration tanks around 100 gallons, 150 to 200 gallons. While those plants are like what Dr. Suzuki told about, there's no external stir. There's not designed for any birthday parties, any weddings. So if you can imagine if you have 15 or 20 person load, and that load is going into a 100-gallon tank, you can think about the treatment result you're going to achieve from that. If you make a filter bed like that, of course you will have a much more enhanced treatment. And also you can pack in the system, so it's a visible system. Most people don't want a treatment system in their backyard full of reeds and stuff, so this is a pretty neat solution where you can just dig the system in the ground. And you can also use as you see here, you can use a pump here for irrigation. Normally the quality come out of these systems are up to bathing water standards. There was a conference by the Agriculture Engineering Society in California in March, and there was a survey presented from United States telling that 50% of the persons with a local septic tank system had absolutely no idea what happened to their water after you pull the chain. No idea what's going on. And I don't know the situation in Canada, but I guess there's a lot of people out there that having a septic tank system that have no idea what's happened to the water after you pull the chain. What was among the only concern then, that if you have septic sewage floating on your lawn, well, people think, wow, that's bad, because then my value of my property is going down. And that was about the only concern they had, that the value of the land would go down, and not that they are contaminating the drinking water or the wells nearby. So it's all a question of attitude to the water, actually. You could have a lot of contamination of on-site groundwater, like I mentioned, with septic tanks or shootouts, with poor treatment of waste and high risk of well contamination. If your septic tank is never emptied, well, there's a chance that you have some leakage coming out of that. The biological treatment, though, offers a better removal of disease-causing microbes, but you also have separation of gray water and black water, maybe best with the gray water treated biologically. What do I mean by telling this? Well, there is a chance, if you see on the compounds of phosphorus, nitrogenous matter, BOD, and COD in the water, you will see the first line coming out from the toilet, the first line with numbers, will give you the numbers of components by phosphorus, nitrogenous matter, BOD, and the second line would be the third line would be the gray water. So we can see the total contribution here in percentage on the last line. You can see that from a phosphorus point of view, you're only 22% in the gray water. For those of you not familiar with the gray water, is the water coming out from the sink, from the washroom, from the shower, and you separate that from the toilet. So what is coming out from the washing machine and the shower would be 23% of the phosphorus, 10% of the nitrogenous matter, 61% of the BOD, and roughly 60% of the COD. So that means if you're able to treat that separately, you have a total different story when it comes to the treatment. So the question is, are there possibility to avoid black toilet water? Well, there is emerging race of new types of toilet based on composting and not water used or limited water used. This is now a proven technology with more than millions of installations worldwide. And I will show you an example of a place called Eco Village in Norway. And the question is this the solution for rural Canada? Consider many rural wells grossly contaminated from on-site sewage treatment. This will show you a situation of some places where we have tested the volume needed for black water and gray water. You see in the first column, you see United States. Second will be Norway. I apologize for not having the figures for Canada, but I would guess it'd be something similar, that the total water you will need would be something like between United States and Canada. What you can see with the separation system with black water, gray water, where you have it separated for gray and black, you see you have a drastic reduction in volume of water. And if you see like an eco village when they're using a compost toilet, you can see the number of water that you actually need to treat, to flush, is far less, and the water coming out of the toilet is far, far less. So the flush toilets are a source of around 20 to 40% of the water use. Disease-causing microbes and nutrients. You have 90% of the nitrogen and 80% of the phosphorus in the wastewater. And you have approximately between 30 and 75 of the organic in the matter in the wastewater. Well, contamination of your own well, it is easy. And from a report from the CDC, we have found that the most disease outbreaks, 64%, caused by untreated groundwater from private wells. A considerable percentage of rural Canada as well are affected by wastewater contamination. And treating water that has been tainted by wastewater is extremely difficult. So maybe some new thinking is required. There's a municipal in Sweden called Tanum. They have forbidden flush toilets due to the damage they're doing to the local community. And for more than 20 years, for 20 years ago, there were like 300,000 composting toilets installed in Scandinavia. it's likely to believe that it's around this time around 1 million. And you have a disease-causing microbes kept out of drinking water sources, and water use is decreased, of course. Well, that's one way to do it. You can see what you need actually is a toilet put up here, and you need a biotank composting tank. It could be a rotating chamber with 2 or 3 or 4. You can rotate it every month. You can rotate it every third month, depending on what is the load on the. If it's a 2-persons building, if it's the 4 or 5 or 6 people living in the house, it would decide the speed of the rotation. How to say about how to use the biological compost toilet. You can put it nicely and neatly inside the house like this, and this is also a photo. I'm not sure if you can see it very well. The toilets are up here, and the tanks or the composting is down here in this section. And it was selected the best roadside facility in Sweden in 2002. Well, as you can see, the 3 first toilets they are available commercially. You can have a composting dry sanitation, which hardly use any water at all. You can have a more sophisticated device with separating the urine from the rest, and they can use that as a fertilizer in agricultural purpose, mixing it with the manure. And you can have water savings toilet with a half liter to 1.5 liter per use. As a Canadian, ordinary toilet could be between 6 and, in the worst case, up to 20 liters per visit. Seeing these figures, you can, of course, figure easily out that there's a huge quantity of water to save that doesn't have to be treated. Said that, I'm drifting into the last part of my presentation. I will say that we also have been working with extensively with industrial wastewater treatment, not only for residual wastewater, but we can apply the biology technology to textile industries, to citrus fruits from fruit plants, canned food, paper plant, even car factories, and runoffs from waste and recycle depots, which is the last photo you see here. There's a filter bed here, taking care of the final polishing of the water. So for larger sewage treatment facilities, different processes are available. Commonly used are processes including various types of lagoons, typical producing effluents in consistently quality. The activated sludge is often used in large facilities. Meanwhile, as biological filtration treatment is a rapidly advancing technology for efficiently wastewater treatment. The processes competing with the biological treatment is, of course, the activated sludge, which is a technology that is almost 100 years ago old. And this process is more complicated and is not as effective. It's still used though, because when land cost is not the issue, it's easy to apply it. But if you compare the size though, since land is getting every day scarce and land cost is getting up, you can see that the size of a biofilter plant is far, far smaller and request far less area than an activated sludge plant would do. On the other hand, you can also see the treatment results for COD, BOD, ammonia, and nitrogen is far, far much better than for the activated sludge, including that you have a great saving in land cost and in size. So it's a much more compact technology. One of the strongest point of view, of course, is it's also environmental friendly. You have very little odor coming out from the plants, the footprints are very small, and you can build nice, neat plants like this from Switzerland, but they like to build them nice up in the ski resorts in Switzerland. If you compare to other systems, a comparison of traditional sewage treatment and biological filter treatment system, the biological system is simpler and a more efficient process. This photo is taken some years ago, though, or this slide. So it just shows you that extension is it's pretty much extended all over the world, this kind of treatment process. I put up a small list of those, of the biggest plant. I mean, this is a plant that is showing you around total treated effluent for 50 million persons. These are huge plants. I mean, a plant like Hannah would be Thunder Bay and Sherbrooke, very huge plant. But if you added all the small plants as well as you saw in the photo for individual houses, you can double that with a tenfold. You cannot double the personal equivalent though, but there's a lot of plants out there. So even if the technology you've seen in Jalakville is very innovative though, biological treatment has proven to work well out with water conditions down to plus 2 degrees. Very short telling you about the configuration of a bath. This is a more technical part. Telling you that you can run them in different mode. You can run them upflow mode or downflow mode. You will have the filter media in the center, and you will need some process here and scur out to backwash it. The important thing here is, of course, the media that you carry the biofilm, and another important thing is the biofilm. As you saw from the very nice video presentation, the previous presentation, you can see how these bugs is growing very fast. And if you don't backwash them, they will just become a huge lump of bugs that will clog your system. So you need to backwash those systems for sewage treatment. Like typical backwashing rate will be 20 to 24 hours. As for drinking water, you can see you can run your plant for weeks without backwashing because, of course, the organic load is far, far less. But the backwashing is the important part of that. You can run it downflow. For the bath technology, you can run them upflow. With the sunken media, you can use them upflow. With buoyant media, you can use open structure media, multi-layer media, biofiltration, or moving bed. Sounds a bit complex though, so I don't want to get too much into it, just to mention that the technology is there. It has been proven in several kind of treatment plants. Starting with the downflow filters, you have filtration with the compact media, but you have a more uneven distribution of the influent. You will also have maybe a sort of accumulation of gas bubbles and shorter filter runs in a downflow mode. If you run it in upflow mode, you will have the water, inlet water coming in from the bottom, passing through a false floor. You will also provide process air and treatment air and flowing in this direction. The good thing about the treated water is up here on this side, so the smell, the odor is gone when you have the inflow in the bottom. You have a more even distribution of water and air. You have a lower head loss development. You have a high velocity. You can run them up to 35 meters per hour, which is a pretty high load compared to an activated sludge plant. And filtration would expand the media, which is not so good, and you will have also co-current backwash though. Well, the solution is something in between the upflow and the downflow. So it's a compromise between those two, but you have a floating media. You can combine the advantages of downflow and upflow. And you will have a filtration that compacts the media. You will have a good distribution of air and effluent. You will simplify the backwash, expand the media. You get no elements of clog though, and easy maintenance. And you would get less media degradation loss and easy odor containment. This is how a compact plant can look like under construction. And this is how we could end up with when you pack it in a mountain landscape. Just to tell you that you can see the ammonia inlet here. This is a sewage treatment plant though. You can see the variation of the ammonia inlet, and the outlet here in the bottom in the green is very low, as you can see, less than 2 or 3 milligram per liter. A typical layout of a plant will be that you have the filter media in this. This is a section of 4 different cells, and you will have the floor of the media, you will have the process air and the scur air in the bottom of the filter. The blue water shows that the water is clean and treated, and the brown here is in the backwash mode because you have to backwash every once a day to get rid of the bugs and the solids that is stuck in the media. Well, the trick is that the large share of the filter media is used by the bacteria to grow biofilm and that transfer ammonia to the final nitrogen, which is actually the nitrogen that is in the air, the N2. I'll just finish with showing you some photos of some bigger plants. This is from Colombia. This is one of the biggest plant. It's the biggest plant of biofilm in the world. It's in Paris, and it's for sewage treatment, though. Here you can see the biofilter plant representing a pretty small area compared to the old existing plants. So biological filtration is also something that you can easily fit into any kind of other treatment plant as a tertiary treatment. If you want to upgrade an existing plant, you can just add on a small unit in the end, or some smaller units to make your plant perform better. If you're out on land, like they do here in Jung'an in South Korea, they have just digging out the sea basin and put the plant outside. So definitely you will be very well off with a small footprint then. Or you can build it in a cavern like a city of Oslo. The treatment plant treating sewage treatment in Oslo is built in the mountains, so you can see it high. Well, going back to the statement I said in the beginning, I think that biological treatment of water and many times biological treatment of drinking water and many times the wastewater can improve the quality of the water within minimum use of chemicals. And that is the key thing, to reduce the quantity of chemicals that you want to use, that you really don't want to use to contaminate the environment. You can also learn by how to adopt biological processes. Sustainable lower cost water purification solutions with minimum environmental impact may need to be cheap for all. So I will finish with this one, and I will bring it all back to you to, when you come back there, to bring the message that to all the people you see that living in your community, to tell them all that if the police will leave the water in the same conditions that you found it, it will be the best for them and the best for the whole community. And like the yellow-kid quails, you can even find the water in a condition and you can turn it into even better conditions. So with that, I will thank you very much for your kind attention.